What other forces do we need?
Gravity.
Gravity. Gravity. 5 times 9.81. Okay, what else? Yep, we got to erase this other roller. We need to kind of understand what is the plane for which the normal is perpendicular. So that's NA, all right? What else?
Friction force.
Okay. And why did I draw it that direction? Yeah, so the friction is trying to get these two rollers to spin in the same direction, so that friction force is pushing the big cylinder in the same direction. Okie dokie. All right. Yes, so I can confirm now that it will work out without using the free body diagram of the other roller. And it'll come out why. Okay, so my steps are known, find, free body diagram, and then what?
Equations of motion.
Equations of motion. Good. Okay, and with a rigid body, I have 3 different options for my equations of motion. I have sum of forces in the x, sum of forces in the y, and then summing moments, usually about g. So let's talk for a second about these first two. The equations are not actually just sum of forces in the x, sum of forces in the y, but they're sum of forces in the x equals m a gx, and then sum of forces in the y equals m a g y. However, tell me about the acceleration of point G here in the x or the y direction.
0.
Why is that, G?
Isn't this just rolling?
Yep. Yeah. So it's not because the problem tells us that this thing starts out at rest, which is actually, I think it's trying to tell us not V equals 0, but actually omega 1 equals 0. Regardless, it's not because it tells us it starts at rest, because it can start rotating with some acceleration over time, but that's going to be an angular acceleration, which is actually asking us to find. But it is safe to assume here that the cylinder is going to stay put in this little pocket. It's just going to be rotating in place. Okay. All right. So for that reason, we know that the sum of forces in the x, sum of forces in the y is going to be 0. Sum of moments about g is going to be I g alpha, and we're asked to solve for alpha. Okay. So why, I'm curious, this is kind of a stretch question for y'all. Why do I know, based on what is shown purely on this page, that we can solve for everything we need to know with everything that's currently on the page? Beautiful. What are my 3 unknowns?
E, M, A, and
Beautiful. Very good. Now, what if we didn't, we do know based on the geometry of the picture, the direction that NA and NB point. But if we didn't know which direction those vectors pointed in, then would we be able to solve?
No.
No. A vector has 2 unknowns, a magnitude and a direction. Okay? We know the direction that these 2 point because we know what direction is perpendicular to the surfaces that they're on because of the geometry of the image. But if we didn't know that, and these were just random external forces working at some unknown angle, we would then have too many unknowns. Okay?
You draw your friction forces their own direction, would it still work itself out?
I want to say yes, but I haven't tried it. I want to say yes, but to be completely and honestly sure, I would want to try it and make sure that it came out right.
Okay. Let me just get in.
I'm not sure. I'm not sure because on this one, because we know that omega is spinning in this direction, it honestly and truly sets the direction that it's gonna
For
roll.
everything else.
Yeah. So like there is nothing else in this problem that incorporates the value of omega and the fact that we know it's rotating clockwise. So there's not like this option for us to solve for omega being in the opposite direction and causing everything else to be the other way. So I think the way that we drew it, I think that has to be correct. Okay. All right. Let's work through this. So let's do one equation of motion at a time. So maybe well, we're actually missing one other thing. We should probably go ahead and set this angle. Oh. So it actually gives us this 45-degree angle here. So I'm going to go ahead and incorporate that into my NA. So it looks like the 45 degrees says NA is 45 degrees to the vertical.
Quick question, Dr. Higgins.
Yep.
We don't assume that the bigger cylinder is also spinning at the same as the wheel because it's going the other way. So we just assumed we assumed it was 0.
No, we assume it's 0 because it tells us that it's initially at rest.
Oh, okay.
Yep. Okay. Let's do sum of forces in the x direction equals 0. What forces do I have in the x direction?
And the.
Oh, I need to tell you where the x direction is.
And the.
Okay.
Sine NA, sine 45 NA. Yeah.
Very good.
And then UK sine 45 positive.
So in case you can't see that, you could essentially draw mu k NA kind of here because we know it's perpendicular to NA. And this complementary angle here is 90 minus 45, which is of course another 45. Okay, so we know this is 45. We know this is 45. So the amount that goes in the x is either sine 45 or cosine 45. It doesn't matter because they're equal. Okay, so that equals 0. We could go ahead and plug in our mu k is equal to 0.2. And that's 2 unknowns, 1 equation. So we can't do really anything with that at the moment. Okay, let's do sum of forces in the y equals 0. What forces do I have in the y? Gravity. Okay.
Positive UK and the.
Okay.
Positive UK and a cosine 45.
Okay.
Positive and a cosine 45.
Yes. This all equals 0. Okay, now I have two equations and two unknowns. So really I could just use these two equations to solve for NA and NB. Why don't you go ahead and do that and tell me what you get?
Mass of the wheel is 5 kilograms, right? Yes.
Yes.
And C is 51.
And C.
C 1. Normal force without C.
Oh, use that instead of B or A. Got it. Okay. Is what, which one?
Yeah, that one was, yeah, I used that instead of C. It's 51.01. And then the other one was 28.9.
I think that's right, but I'll double check. Yep. Close enough. You'll notice that when I do my notes, if I use N as a force, I am very careful to write out the Newton because it can be very easy for the Newton unit to magically become the N force, which will cause all sorts of chaos. Question, Micah?
I think it is about the numbers.
Okay. Okay, but that still doesn't tell us what alpha is. So alpha shows up in our sum of moments equation, so we'll do that one next. So sum of moments about G equals I G alpha. Okay. So which forces cause a moment about G?
Only friction.
Only the frictions, correct. Both of the normal forces point directly into G, and so does the mass. So it's just this mu K NB and the mu K NA. And then I needed to put the radius of the whole thing, which is 125 millimeters, which is annoying, so 0.125 meters. Okay, so let's do the friction at B. Is that a positive or a negative moment?
Negative.
It's a negative moment. Very good. So we need mu K NB times 0.125 minus mu K NB times 0.125. Okay. Tell me about friction at A or GOC.
Sorry. That one's positive.
That one's positive. Very good. So plus mu K N A times 0.125 equals my corrected IG, which is 1/2 mr squared. Times alpha. Okay, let's plug some stuff in. Should have minus 0.2 times 28.9 times 0.125 plus 0.2 times 51.01 times 0.125 equals 1/2 times 5 kilograms. Yeah. Times 0.125 squared equals alpha. Or no, sorry, times alpha. Jeez. But one equation, one unknown. Just solve for alpha. What do we get?
14.2.
Check. Yep.
Closest the rounding have to be on these.
I prefer it to be 2 decimal places, but to be honest, I never actually grade that way. I usually grade more leniently, like 1 decimal place. Yep. Okay, so this was like beautifully fell into the known fine free body diagram, equations of motion, solve system of equations, and you're done. Sometimes we have to use an extra kinematics equation. This one we did. Okay. Okay. All right. Questions about this? How do we feel?
Could you go over really quick how the friction force goes in the same direction as like the motion for at point like A or C or whatever?
Yes. So for the roller A, we need to think about the fact that the big cylinder is starting out with no motion, right? Starting out with no motion. But A is over here spinning like a fool with omega. So it's already going over here with omega going in this direction. So you can actually, if you're like a physical intuition kind of person, you can think about putting your finger on a roller that's spinning. Which direction is it going to push on your finger? Is it the direction that it's spinning or the opposite of the direction it's spinning?
Is that a like rhetorical question or?
No, I'm literally asking you to intuitively think about it. Tell me.
I mean, probably in the direction that it's going.
Yeah, right? You're going to feel it like wanting to grab your finger and push it in the same direction that it's going. So it's going to do that same thing to this cylinder over here. It's going to say A is just spinning, spinning, spinning. And when the cylinder comes in contact, it's going to say, hey, you're coming with me, right? You're going to move in the same direction that I'm moving. And that thing that you're feeling is the friction pushing on the cylinder in the direction that it's wanting the cylinder to move.
Okay. All right. I get it now. Thank you.
Yep. So because A is like injecting energy into this cylinder, this A is causing the cylinder to start moving in its same direction. We know that this cylinder will eventually start rotating that way. And it's that rotation in this direction that causes it to rub against the wall at B. So it's wanting to move, these particles are wanting to move downward, but the friction at B is going to resist that downward motion of these rotating particles. And so the friction at B is going to try to oppose that motion and point up. Does that help a little?
Yeah, that makes more sense. Thank you.
Okay, great. Okay, anything else?
I have a question. This was on homework 7.
Okay.
I guess it's this topic.
Yep.
At some point you used it's the roll without slip equation, I think, which is acceleration equals R under acceleration. Was that
Yeah.
because like
Let's talk about it. I'll pull it up.
Yeah. -3?
It's this one. Yep. Okay. So I use the equation that looks very much like roll without slip.
But it's not roll without slip.
It doesn't, it is roll without slip, but the reason that it's roll without slip is because anytime, like if you have a bobbin of thread and you take it and you pull it and this thing starts to unspool exactly at the same rate that you're pulling the thread out, or like a yo-yo, it's moving down only as much as the rope allows it to go as it unwinds. That unwinding or even winding up, where a rope is perfectly aligning with the circumference of something that is turning, it's roll without slip that's happening specifically for that radius and that string.
And because that's a spool, the spring is like doing that motion.
Yes.
That's why you're using, okay.
Yes,
That
but
makes
you
sense.
have to use the radius that the string is wrapping around, not the radius that is rolling on the ground. right?
Yeah.
It's because it tells you that it's slipping at A. It tells you it's slipping at A. So it's absolutely not omega times 0.6. That's the wrong R. But because it's spooling out perfectly at that 0.3 radius, we get that same relationship that holds.
That makes sense.
Okay.
If we are given, I don't think we're gonna ever, I mean, maybe, but if we're given that the spring doesn't roll like that, would it still be solvable?
No, this one relies on you knowing that relationship.
Okay.
Yep.
The solutions are posted, right?
Yes, I just posted it this morning because I just finished this detailed guide this morning. The Hibbler solutions were up earlier. They were already up, but I like mine better because I'm selfish.
Wait, where can I find this one on Canvas?
In the same module where homework 7 assignment is posted,
Okay, thank you.
is the solution guide. Originally, it was the Hibbler solution guide, but I just updated it today to be my solution guide, which is much more thorough.
Gotcha, thank you.
I've been basically doing that all semester. In previous semesters, I only posted the Hibbler solutions, but my extra work for this semester has been to try to make my own solution guides to make it easier to follow. Okay. All right, what's next? Any other questions?
Is there a reference plan in like the moving, because we did like with the ant and the frisbee one? That's not.
No, that's not on this one.
And we have any moving reference frames on this?
You choose where you put your reference frames, so it is possible to choose a moving reference frame.
But it won't be like an ant and the frisbee one where you have to. like-
No.
It won't be the intent problem. Okay. That was what I was asking.
Doesn't it affect though, like it's slipping though, like it is affecting the amount that that the school is releasing cord, whatever, right? Like,
It is, but only because of this friction force.
Yeah.
This friction force affects all of the accelerations, right? The fact that there is friction happening between A and the ground affects all of the relationships, but there's still a relationship that holds between the acceleration of the center of gravity point and the angular rotation of the body. And that holds because it's being spooled out. So both of those things can be true at the same time. Okay, do we want to perhaps go back to Jeopardy and look at the other new problem? That's not new, we did that one. I added this. Oh, sorry, you guys can't see it. I'm stupid. Okay. Let's add a new page, take a picture. All right, do we want to do this one or do you have other questions? Let's do it. Okay. Alrighty. Okay. Let's do our known. Marble having a mass of 5 grams, which is going to be annoying to work with. So let's get it to kilograms. So 1, 2, 3, 0.005 kilograms are dropped from rest at A, V equals 0, through the smooth glass tube and accumulates in the can at C. Determine the placement R of the can from the end of the tube?
We're assuming R is in the middle of
Or would just be the landing point at the exit point because it doesn't collect the size of the can.
Yep, it's just the landing location.
Precisely.
Okay. So just like almost every other problem in this class, there are many different ways that you can do this. I'm going to do this in 2 steps though. I'm going to start out by trying to analyze or trying to figure out what the heck is the velocity at B. Like what is the velocity of this thing when it leaves B? And then I'm going to do the projectile motion part of the problem, which covers the motion from here to here. So what I'll do this step 1, step 2. For step 1,
Would it be, G equal
back up a second and tell me what equation you're doing that for.
the not just like the T equals U from 1 to 2 equals T.
Work energy. You could actually use either one because there's only conservative forces doing work. There's no friction. Literally, the only thing happening is we move in the direction of gravity. Yep.
I remember in the last recitation, I asked like this question, if you could use this one always. Is there ever like a advantage to using the other one?
Yes, I believe there does exist a problem in the Hibbler book where it is much easier to use conservation of energy. I can't remember which one it is, and I can't remember why.
So, because I just
But
like,
it's always going to be. I believe it's always possible to do it with work energy. It just might be a little bit more work. I believe that it's always possible. Okay, so you want to do work energy?
I don't care.
Let's do work energy.
Because I mean, would it? No, am I wrong? But sorry, I said page. No, like.
No, we can absolutely use work energy. Okay. So what is the kinetic energy of this marble at A? Yep, we're starting from rest. We're released from rest. What all things are doing work on this particle from A to B? What all forces are doing work on A?
It's just gravity, right?
And we could draw a free body diagram to do that. However, the normal force is going to seem a little weird because what you might think that the normal force is doing work here because the ball does displace from left to right. But the normal is instantaneously always perpendicular to the motion. Right. It never does work because the direction of the normal force is always changing. Now, if there were some external force that were always to the right, no matter where it was on the tube, that force would have done some work because this thing went from left to right. But the normal force itself, it rotates with the location of the ball such that it never does work. So truly only mg does work. Okay, now is mg doing positive work or negative work? Positive, yep, because we're moving downward, mg points down. And then what is the height change? 1 meter, because it's 3 meters minus 2 meters. And then kinetic energy at the end is 1/2 mv 2 squared. Our masses cancel, so those don't really matter. We got 9.81 equals 1/2 times V2 squared. We should get V2 equal to, oh gosh,
4.43.
4.43. Yep. Ah. Meters per second. Okay, so notice, however, that this is a speed. Work energy is a scalar equation. It doesn't tell me anything about the direction. However, because of the geometry of the problem, we can tell that it is initially moving vertically and finally moving entirely to the right. So this entire speed at B, or at point 2, is entirely to the right. Okay, so when we go to do step 2, which is projectile motion, we know that the initial velocity for this step is equal to the entire speed only in the I hat direction, once I tell you what is the I hat direction. Okay, so we have 4.43 I hat meters per second. You're looking at me like I have 3 heads. Oh, okay. Is that computing?
Yeah.
Okay. So now we have everything we need to do the projectile motion part of the problem, which you should know how to do. So I'm going to step back and let you work on that. Try to solve for R. I'm gonna go to the bathroom because I'm pregnant.
I'm like talking with someone and it just like comes out of nowhere and just cuts us both off and starts talking. Yeah, it's a yapper, bro. I had insurance with him and Dr. Morgan did too. It was the funniest thing.
Cause this stuff isn't, I think it's gonna kill me, so stupid, like going from art to end data like stuff and just getting the stupid like.
Do you think that'll be on there? I think so, so that's chapter 13, isn't it? No.
That's what I got. I hate this, I hate the projectile motion stuff. I feel like it's like you're always one step away from getting shit.
If it's like this stuff.
This stuff is not that bad. This one wasn't that bad. Yeah.
The whole, some of them have me dying.
Bro, no, it was like, I was stressed and I was like, bro. Retarded.
But like, I mean, she posted the answers, so I'll go through that later, but I gotta go back. Okay, to jump in, it's like another graph for your, module 2. Like of your data.
Yeah, we chart.
Okay.
Yeah.
Because we didn't really need to plot them. Do you guys want me to plot them?
No, I think you did. What did you do?
I did not plot the, or I just changed the plot given our new, I changed the
Yes,
graph given
that's
the
what
new
I did.
R data, or,
Yeah, sure, like in like prediction.
yeah. we tried to-
Oops. Okay, so when we integrate for position, it's important that we know where we're putting our coordinate system. And so all of the decisions I am making are based on a coordinate system that's located here. Okay, so I'm saying that my initial position is 2 meters up in the air and at 0x. And my final position will be at 0y, but r in the I direction. Okay, so these decisions depend on where you place the coordinate system origin. Okay, so let's see. I'm probably gonna skip a couple steps here. Let's do 4.43 t I hat minus 9.81 over 2 t squared j hat equals r I hat minus 2 j hat. Okay. So I'm seeing two equations and two unknowns here. So one will be our I hat equation. So 4.43 t is equal to r. And then our j equation will be minus 9.81 over 2t squared equals minus 2. So we should be able to use the j equation to solve for the time. We should be able to use the I equation to solve for r. Okay, do you have final answers?
To it,
For what?
for T, 0.6386. Yeah.
Seconds, and then r is meters. Okay. Yep. Very good.
Excuse me.
Yes.
Can't you also just treat it as like a cliff problem with all the like velocity in the horizontal direction to find the horizontal distance?
I'm not sure I'm following what you mean. What do you?
Well, because I'm saying like for like projectile motion, like that, because that's what I did, and I got the same exact answers, but I didn't have to like I didn't do any integration or anything.
You just did the big kinematic equation, like the.
Yeah. You just pulled the equation off the equation sheet. Yeah, that's fine. That's fine.
Oh, okay.
But the reason I always redo the integrations is because I want to hammer home this fact that acceleration here is not necessarily always constant. It is always constant for projectile motion because the way that we define projectile motion is like we ignore air resistance and we assume that the only force acting on this body is gravity. And because of those assumptions, the acceleration is constant. Okay, so the equations in the textbook or the equation sheet hold only for constant acceleration. So they do hold here. But in real life, for a projectile motion problem, it's probably not going to happen in real life that you ignore air resistance for, I don't know, I have a lot of people who are really interested in like aerospace. Those aerospace, cars, vehicles, anything that is moving at that type of speed it's going to be completely stupid to neglect air resistance. So as soon as you decide not to neglect air resistance, suddenly acceleration is not constant. And so the way that I rederive everything is still completely holds for those situations. But the way that you went and got that equation out of the textbook will no longer hold in that case. Okay, so I like to hammer home the integration because we're engineers and we should be comfortable with integration at this point. And this method works in more cases than grabbing that equation from the textbook.
All right, sounds good.
Does that make sense?
Yeah.
Okay, sounds good. Okay, what else we have? Oh, we have like 5 minutes. So I guess we have time for any random questions. Probably can't do a whole nother work through, but
Could you briefly go over the practices and like plain one? Like it has the worked out solution. I just like just go over like the free body diagram for that.
let me pull it up.
Question two.
Oh, yeah, okay.
Because the question asked the normal force of the person on the seat, so that part just kind of tripped up. Like as far as like trying to visualize it.
The normal force that the person exerts on the seat.
Yeah.
Okay, well, it's always gonna be just a difference of positive or negative, right?
Right.
Between what he exerts on the seat or versus the seat on him, right?
Okay.
So as long as you recognize that like the seat is keeping him from flying off in the, like the,
Into the abyss.
right, into the abyss, into the outside of the curve.
Yeah.
Then you should get the normal, correct?
And then it's just, okay. Okay, yeah, I was just like, I don't know, I said it and I'm like, yeah. That's really-
And in fact, I think the way they drew this free body diagram is actually, I mean, the free body diagram here is correct, but that's not what the problem is asking you for. It's asking you for the negative of n.
Yeah.
I don't really care about that too much.
Okay.
I care about what's shown on the page.
Okay.
Gia?
For the third one in the problem, I didn't understand why they like drew another free body diagram. I didn't do that and I still got the same answer, or I mean. What was it? Yeah, I got 88.2 instead of 88.3,
Yeah, you're fine.
but I was like, I
Okay.
don't know why they redrew it.
Yeah, I got another question about this. This is, okay, so the equation we know in this class is sum of forces equals mass times acceleration, right? And we learned how to draw a free body diagram, which represents all of the forces as arrow vectors, right? So what we essentially learned to do is draw a diagram for the left-hand side of that equation. What other professors will do, and is probably more complete and more accurate to do so, is to teach you also how to draw what's called a kinetic diagram, which is a diagram that represents the right-hand side of that equation. So in that case, you're drawing arrows that represent all of the accelerations that are happening.
Which is what the other.
Yeah, that
Which
makes
is what
sense.
that right-hand side is showing. I don't teach kinetic diagrams anymore because I just don't find them all that useful. Because more often than not, you can absolutely do the problem without it. A free body diagram, on the other hand, is like absolutely essential to get all of the trig, all of the forces, making sure you're incorporating everything. It's almost impossible to get the problem right without a good free body diagram. But I have almost never needed a kinetic diagram to truly understand what's going on in a problem. So what they incorporated into this diagram is the fact that this thing is doing fixed axis rotation. But as long as you recognize that this thing is doing fixed axis rotation, and you recognize that that means that the point G would accelerate both in the X direction and the Y direction, and there would be some alpha, and you need to go grab the fixed axis kinematic equation from your equation sheet, you're golden. You'll get the problem right. You have to recognize those things, but you don't need them on the free body diagram to show you that. Or on the kinetic diagram to show you that. So this is where one of those things that's like a difference between the way that Hibbler is canonically taught versus the way that I teach it, and the fact that like if I had done the full written solution guide here, I wouldn't have shown that and you'd still get the problem. Sound okay? Okay. Anything else? We got 2 more minutes.
Someone typed out a question in the chat.
Oh, thank you. I really appreciate the heads up. Will there be conversions between coordinate systems on the exam? Like, that is completely fair game. Yeah, absolutely. That's like a, I consider that to be a baseline skill that you should know at this point. Anything else? You're welcome. Just another heads up, I updated the equation sheet. So the equation sheet that is currently on Canvas now reflects what I will be giving you in the exam. The only thing that I changed is I used to teach the SVAT relationships. You might have seen those on the equation sheet. We never covered them. I don't teach them anymore. I don't find them that useful. So I took that off in order to make extra room for the additional things that I told you in class that I would add. So things like the equation for the radius of gyration. I think I put the parallel axis theorem and I put the equation for the radius of curvature on there. Okay, so I added those 3 things. I took off a section that you no longer need in my class. But what is currently on Canvas is now up to date. And I am about to go print them off as soon as I can get back to my office, which is actually might not be today. I will have them printed. Okay, the exam is structured like exactly the same way as the last exam. So 5 concept questions were 2 points apiece, 3 work through problems were 30 points apiece.
And as far as like the point spread, just make sure we're pretty much writing everything.
Absolutely, you have to show your work. It's the only way I can give you partial credit. And it's all, I mean, it's also how I know that you didn't cheat. Because if there's no work and then there's suddenly the correct answer, it's like, how the hell did that get there?
He's just using his calculator. I don't know how it goes. He just like looks at the problem with his calculator.
There are some people who can do that. I don't know how to grade that. I honestly don't.
Crazy.
Some people can do it, but I don't know how to grade that.
It's the headphones.
Locked in.
It's a flow state.
I get it.
He's got like birds of fire.
Okay.
This is
All right, I'm gonna log off Zoom. If you have any other questions, please do feel free to email me, okay?
Thank you, Dr. Higgins.
Thank you. Bye.